Hi, everyone. Well, let's pick up our discussion after a little pause. You can see it's daytime now. All right, so I'd like to turn now to talk about angular momentum. So something really important about central potentials, or spherically symmetric potentials, is that in such systems, angular momentum is conserved because there are no forces that act in the angular directions in order to change it, to exert torques. Okay? Now, we've already talked a little bit about angular momentum. We introduced quantization of angular momentum in the Bohr model. But now we'll see that in the full quantum mechanics treatment, angular momentum is a little bit more complicated. Not only is the magnitude of the angular momentum quantized, but its component along one direction is also quantized. Here, you'll see what that means in just a moment. But those quantizations are determined by the two quantum numbers L and M. Here, let's turn to the notebook. Okay, so remember that in the Bohr model, angular momentum was quantized in the following way. L equals n h bar, where n was an integer. Okay? In quantum mechanics, on the other hand, it can be shown that angular momentum is quantized in the following way. The magnitude of the angular momentum is given by square root of L times L plus 1 times h bar, where L is the angular momentum quantum number, which can take on values 0, 1, 2, 3, and so on. But and you can see this looks a little different than what we had in the Bohr model. On the other hand, there's another condition. The component of the angular momentum along one direction, here the z direction, is also quantized. So that mz is equal to m sub L times h bar, where m is the second angular quantum number. It's the one that determines the shape of the wave function in the azimuthal direction, remember? And here, m sub L can be equal to 0, or it could be plus or minus 1, or plus or minus 2, but it's subject to a constraint. The constraint is that the magnitude of m sub L must be less than or equal to L, okay? So these conditions show how angular momentum is actually quantized in quantum mechanics. And the meaning of this is kind of interesting. I'm going to turn to a PowerPoint to show you some slides. 1 second. Very good. So, excuse me. There we are. So the magnitude of the angular momentum is quantized according to this condition. And the z component of the angular momentum is separately quantized here with the quantum number m. L can take on integer values, and m takes on positive or negative integer values, but the magnitude of m must be less than or equal to L. Okay? And these are the z component and the magnitude of the angular momentum. Okay? So there are a couple of things about this that are interesting. First, let's try and imagine what this means. This means that, so in this drawing, the magnitude of the angular momentum corresponds to the length of the vector, the blue vector shown here. And then the z component, shown here, the z component together with the magnitude determine the orientation of the vector in the polar direction, okay? So that, for example, if L is equal to 2, then M sub L can take on these values, -2, -1, 0, 1, or 2. And those different orientations are shown here. Okay? Very good. So there are some things we can see immediately. For example, we can immediately see why the magnitude of M has to be less than or equal to the magnitude of L. Otherwise, it would be possible for the Z component of the angular momentum to be larger than the total magnitude of the angular momentum. Of course, that's not possible. Secondly, we can see something interesting. The orientation of this, not only the magnitude, but the orientation of this vector, angular momentum vector, is itself quantized. The polar angle that describes the orientation of the angular momentum vector is theta. And of course, we can see immediately that cosine of theta is equal to Lz divided by magnitude of L. And so that's given by this term, M divided by square root of L plus 1. Okay? That means that there are only certain directions that this can point. For the case L equals 2, and M sub L can take on any of these values, and the possible values of cosine theta are given here. There are exactly 5 of them. And those correspond to a specific set of angles. Okay? And those are the only polar angles allowed for the angular momentum vector in this system. Wow. Something else, which I'll mention, although it kind of goes beyond what we're really covering here, is that if the Z component of the angular momentum is specified, as it is here, then it turns out that the X and Y components of the angular momentum are unknown. There's actually an uncertainty principle between the different components of the angular momentum, something you'll learn about in a later course. So this drawing is kind of nice because it shows that the polar angle is if the polar angle is specified, so that the Z component of the angular momentum is specified as shown here, then the X and Y components of the angular momentum are unspecified, are unknown. And so in particular, the azimuthal angle phi is unknown. Okay? Very good. So this is kind of strange, but it's a consequence of the fact that the magnitude of the angular momentum is quantized and the Z component is separately quantized. Okay? Sometimes this is called space quantization. Since what we're doing is we're specifying the different values that the orientation of a vector can take on in space. All right.